So we've been looking at the relationship between the rate of a reaction and the concentration of a reactant, and we learned about reaction order and rate laws. So now we're going to talk about the integrated rate law. And if you've had calculus, this means what you think it does. It's the rate law, but integrated. If you haven't had calculus, that's fine. You don't need to know any calculus to do this work just fine. But the integrated rate law gives us the relationship between the concentration of a reactant and time, and that's a lot more useful than the rate versus concentration. So the integrated rate law, like the regular rate law, is going to depend on the order of the reaction. So first order, again, talking about a very simple decomposition reaction. First order rate is equal to the rate constant times the concentration of A. And we learned on the first day that we can define the rate as negative change in A over change in T. So then we can set these equal to each other and say negative delta A over delta T is equal to Ka, and this is what's known as the differential rate law. And then you integrate that and you get the integrated rate law. So this can be expressed in two ways. This is kind of the normal way you see it. The natural log of A at time t is equal to negative rate constant times time plus the log of the concentration at time 0. It can also be expressed this way. So A with a subscript of t means the concentration of A at time t. A with a subscript of 0 means the original initial concentration. Okay. So if we graph this, and this equation is in the form of a line, y equals mx plus b. So if we graph y, natural log of A at time t, versus time, several jumps there. There we go. So t is our x value here. Then we see that the y-intercept will be equal to the natural log of the initial concentration, and the slope is going to be equal to negative k. So the slope of this graph is negative, but the rate constant is positive, okay, because the slope is negative k. Any questions about that? So let's look at an example. We're going to look at the equation for the decomposition of SO2Cl2. So they monitor this concentration at a fixed temperature as a function of time. So here we have time 0 to 1500 seconds, and they've measured the concentration of the reactant at each of those times. So this is asking us to show that the reaction is first order and determine the rate constant. Well, earlier when we tried to determine the order of a reaction, we had data that gave us initial concentrations that were different and measured the rate, right? And we looked, well, does the concentration double and the rate double? Okay, then it's first order. We don't have that sort of information here, so we can't use that approach to determine if it's first order or not. So what you would do is you would graph the data. So if you suspect that it's first order, you want to graph natural log of A at time t versus time. So you'd have to do some calculation, right? So you'd need to calculate the natural log of the concentration at each of those times. So this first one would be negative 2.303. And what we're going to learn in lab today is that if you have something like this, you don't punch all these numbers into your calculator. You put the data into Excel, you type an equation in once and copy it, and it does all the calculations for you. It really is a beautiful thing. So to do this, we would need to graph the data. I'm not going to graph the data in class because that would be tedious. So we're just going to look at the graph. So here we have natural log of the concentration versus time. We have a negative slope. We have a straight line. That tells me that this is a first order reaction. If it was any other order, it would not be a straight line with a negative slope. Okay? So we graph that, and then they were asking us to find the rate constant. So the first order integrated rate law looks like that. So this here's the rate constant. And they're giving units of reciprocal slope, or 1 over S. We could get that from the graph by looking at, when we calculate a slope, it's the rise over the run. Here, the rise has no units because it's a logarithm, and so it's no unit over S. And you'll also see, if you look back at the notes from last week when we found what are the rate units on the rate constant for first order reaction, it's 1 over second. Okay, so here we have that same graph, and this is saying to predict the concentration of SO2 Cl2 at 1900 seconds. So if we're looking at this graph, it does not go out to 1900 seconds. So we can't just read it off the graph, right? Because it didn't go that far. What we're going to do is we're going to use the equation for the line. So y is the natural log of the concentration. T is the time. The intercept is the natural log of the initial concentration. We don't even need to recognize that at that point. That's just going to sit there. Let's go back to purple. So y equals negative 0.000 290 times t. Well, we're looking at 1900 seconds. So put 1900 in there. Plus, no, not plus, minus 2.30. And then we're going to solve that for y. It's okay. So y is equal to negative 2.851. Is that the concentration?
No.
No, it's the log of the concentration. So that's equal to the natural log of the concentration. Well, how do we undo natural log? Log, the anti-log is 10 to the x. For natural log, the anti-natural log is e to the x. So there's a button on your calculator that says e to the box or e to the x. So I'm going to press that, and I'm going to type in the answer I just got. And, oops. My calculator shows me all of that. So that's one way to solve the problem. Another way is to say, well, instead of just calling that y, I'm going to say, well, that's the natural log of S2OCl2. And you could type this into the number solver on your calculator and put x in for this guy. So for that guy right there, put x into the equation and let the calculator solve it for you. Does anybody want to see how to do that? Yeah. Okay. Let me get out the Elmo here.
We set x to 0, right?
Yeah. It's always a good idea to start with x equals 0. I'll write this on the board because otherwise I'll forget it. So we're doing natural log of x is equal to -0.00090 times 1900 minus 2.3. No, just 3. Okay, so what I want is this number solver. So a second num solve, and it's just remembering the last thing I did. So I'm going to press clear and move my cursor to the right and press clear, so I have a blank screen to start with. So on the left side, my equation says natural log of x. So I'm going to do natural log, and then this button here with all the letters on it, that's the variable button. And I'm going to close the parentheses just because it bothers people. And then over on the right, I have negative 0.000290 times 1900 minus 2.3. Right? I type the equation in. I'm going to press enter. I'm going to tell it to start with 0 and let it go. 0.057786505. Exactly the same answer that I got using algebra. Anybody having any problems with their calculator doing that? I'll come and speak harshly to your calculator. It's your calculator's fault. It's not your fault, right? Calculators misbehave all the time. Any questions about that one? Yeah. How did I do it? Okay, so the first thing you want to do, you see this numSolve button? So I do the second function to get the number solver. And if there's something in there, you just need to clear it out. Okay. And so then I'm typing in this equation, right, where x is the thing I'm trying to find. So I just type it in just like it looks. And when I get to the part where oh wait, x is right at the beginning, never mind. The x in here, that guy, comes from this button. So I could make it y, z, t X is just what happens first, and so I just usually use X. So you type it all in, you hit enter, and then it's generally a good idea to start with X equals 0. It solves this by iteration. So it's going to take the value that you give it, and it's going to plug it in and find out, well, that doesn't work. And so it's just going to adjust and just keep going and going and going until it gets the next one. Did that help? Yeah. Any other questions? Okay, let's go back to this. So these are all the digits that my calculator showed me. Is that a reasonable number of significant figures? No, it's not. So what do you think would be a good number of sig figs? 3. If we look at the slope, it's got 3 sig figs. This number has 3 sig figs. The 1900 seconds here, it's like, well, do they really mean that they just estimated it to the nearest 100? Probably not. They're just probably being sloppy. So a good guess would be 3 significant figures. And in this class, the good guess on sig figs is generally just fine. So 0.0578. Well, I don't want that to say X there. I want it to say the concentration. And what would the unit be? Moles per liter, molarity. One thing that is important with sig figs and rounding is if you're going to use that number in a future calculation, use extra digits, okay? Otherwise, you can get rounding errors, and they can be pretty extreme sometimes. So what I do when I write down the number that my calculator gives me, I think about, well, how many sig figs do I think I'm going to need? I think I'm going to need 3, and so I'm going to write down 2 extra digits, just the next 2. You can round that 6 up to a 7, or you can leave it as 6. It really doesn't matter. If you keep 2 extra digits, it saves you from rounding errors. That's not good for the pencil. Any questions? Okay, here's another one. Cyclopropane rearranges to form propene. In the gas phase, the reaction's first order in cyclopropane. And they're giving us a measured rate constant at a temperature. I'm saying if the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235 minutes? There's a whole bunch of words in there. Dang it. Well, it can be helpful to highlight these numbers. You may or may not need all of them. But let's identify what they are. So that first one, it says rate constant, right? So that's K. And then it gives us a temperature. Have we used temperature in these calculations? No. Why are they telling us what the temperature is? They're telling us the temperature because at a different temperature, the rate constant will be different. For this problem, do we care what the temperature is? No, we don't care at all. So we're not going to use the 720 Kelvin. So if you look at previous problems, they said at a particular temperature, or at a certain temperature, right? They didn't actually tell it to us, but they're specifying, okay, at this temperature, this is the rate constant. So the 720K is important, but we don't need it at all. And so it says initial cyclopropane concentration. So I like to just use A. So that would be A0, where A is representing cyclopropane. And so that's the initial concentration. And then it says, what's the concentration after 235 minutes? So that's our time, 235.0 minutes. So it's a first order reaction, so let's write out the integrated rate law for a first order reaction.
Will we have to put those minutes into seconds?
Yes, we will. So we always want to write down our units. So here, this is per second, and the time is given in minutes. Those units need to agree. Sometimes you'll find that the rate constant is per minute, and then a time of minutes works out perfectly, but they do have to agree. So we need to convert that to minutes. So there's 60 seconds in 1 minute. One, 4, 1, 0, 0 seconds. So what we're looking for is A at time t, where time t is 141.00. Here we have the rate constant, so we can plug that in, we can plug this in. We know what A0 is, so we can fill that in. So natural log of AT is equal to negative K, negative 3.36 times 10 to the minus 5, oops, s to the minus 1, times 14100s, plus natural log, I don't have enough space, natural log of 0.0445. Any questions? Yeah.
I'm actually confused on the natural log. Like, why are we adding the natural log?
Why are we using the natural log? That's a great question. So that comes in back here through the magic of calculus.
Okay, so that's the integration.
That's the integration part.
Oh, okay.
And, you know, if you like calculus, good for you. I liked calculus when I took it, but do I remember how to integrate that differential rate law? No, I don't remember. I don't remember. Could I relearn it pretty quickly? Yeah. Do I want to? No. So that's a great question, but that's why natural log comes in there. Any other questions? So again, we need to solve this. Our answer is A of t. So you can solve this using algebra, or you can solve this using the number solver on your calculator, which we'll demonstrate that one more time. So natural log of x do that right? So let's go back to the Elmo. Unfortunately, the Elmo doesn't show up in the video recording of the lecture. I'm gonna get that num solver. There's that same equation I used before. And it's like, oh, natural log of x. That's what I want. I don't need to clear that and type it in. You can. I'm just gonna skip over to the other side and get rid of that mess. And so I want negative 3.36. If you have not learned how to use the scientific notation button on your calculator, please learn it right now. This button, EE, that's the scientific notation button. So I want 3.36 times 10 to the negative 5. So I'm going to push that button, and as I push it, I say in my head, so people don't think I'm crazy, times 10 to the negative, times 10 to the, and then I put in the exponent. Yes, the button says EE, and when you push it, it only displays E on the screen. That's fine. This saves you a lot of keystrokes, and also saves potential problems when dividing by numbers in scientific notation. Every time you push a button, you have an opportunity to make a mistake. Right? So negative 3.36 EE minus 5 times 14100 plus natural log. And on this calculator, the first time I push this, it gives me natural log. If I push it again, it changes it to base 10 log. And then I can go back to natural log. Oh, no. It's going to go to some other base and then back to natural log. And so in there we want 0.0445. I'm going to have it start at 0. 0.0277. I think that's it. And I probably want the 3 sig figs. I'm going to write down the next 2 digits. 0.8. And then I'm going to report the answers 0.0277 molar. Any questions? You do not have to use the number solver to do these. But if algebra, especially algebra with natural logarithms in it, is not your friend, I would recommend giving this a shot. Any questions? Oops. Yeah.
So once we do the natural log, then the natural log drops, and it's just a concentration of T, so you end up with.
Oh,
Yeah, so when you put natural log of x into the number solver, it's going to return just x. If you do this in a more traditional way, where, you know, okay, well, this is equal to all these numbers, I'm going to do the math for all those numbers. Then you're going to have the natural log of a. So then you need to do e to the x to both sides to get rid of the logarithm. You'll end up with the same answer. Yeah. Any other questions? Okay, what about the second order? So, again, looking at a simple decomposition, here's the rate law for a second order reaction. It's the concentration of the reactant squared. We can also say that the rate is negative delta A over delta T. Yeah, question?
I didn't get the number, I don't know.
You didn't get the number, okay.
I think it's probably something.
So then you can say that this is equal to that, gives you the differential rate law, not very useful. The magic of calculus gives us this. This is the integrated rate law, written in the form of an equation for a straight line. So this tells us that if we graph 1 over A, 1 over the concentration on the y-axis, and T on the x-axis, we're going to get a line. We're going to get a line, and the slope is going to be equal to the rate constant. The intercept is going to be 1 over A0, the initial concentration. Okay. This one is 1 over concentrations instead of natural log concentrations because of integrating in calculus. And for most students, you don't want to know any more than that. So here we've got another decomposition reaction, decomposition of NO2, monitoring it at a fixed temperature. They're not telling us what the temperature is, but they throw that in there because it's important. If the temperature's changing, your rate constant's changing, the data doesn't tell you anything. So they're just, it's like the fine print on a contract. So they monitor the concentration as a function of time, tabulate the data, show by graphical analysis that the reaction is not first order and that it is second order, determine the rate constant. So we've got this data here. So to show that it is not first order, we would graph it using the integrated rate law for the first order reaction. So we would calculate the natural log of NO2 and graph that versus time. I think I did that, yeah. So here it is, the natural log of NO2 versus time. And you can fit a straight line to the data using something like Excel. But does this data follow that line? No. It's high at the beginning and high at the end and low in the middle. It's not a line, it's a curve. Your data points will not always be right on the line, but if it's linear, they're going to be scattered equally above and below the line. So this shows me this is not first order. For the second order graph, again, we have to do a little bit of calculation. So back here, we take this concentration, 1 divided by that. 1 divided by this, 1 divided by that. We would do that for all of those and then graph it. And this gives us a nice straight line. Linear regression tells us that the equation for that line is y equals 0.255x plus 100. Can't remember what's on the next slide. Okay. Oops. Most of the questions on the exam are multiple choice, and I do believe in some evil in making up the distractor choices, but not truly evil. So I'm not going to give you this as one answer and this number with the wrong units as another answer. That's too evil. I will give you an answer caused by a common mistake. Like if you got negative k, I might throw that one in because you're like, oh, well, the slope is negative k, but that's a first order, right? So I might throw some things like that in there, but I'm not going to try to trick you on the units, okay? So continuing with that problem, use the graph and best fitting line to predict the concentration of NO2 at 200 seconds. So T is 200. Sorry, 2,000 seconds. Well, this is our equation for the line. The integrated rate law is 1 over AT is equal to KT plus 1 over A0. So the equation given on the graph corresponds to the integrated rate law. T is x, and y is 1 over the concentration. So 1 over the concentration at 2,000 seconds. 0.255 times 2,000 plus 100. And so we can do that on the calculator, the more old-fashioned way. 0.255 times 2,000 plus 100, and that's going to equal 610. Is that my answer? No, that's 1 over the answer, right? So 1 over AT is equal to 610, which means that AT is equal to 1 over 610. Zero 0.0016393. It's a pretty ugly 6. So the algebra on that one is not as tricky, no logarithms, but you do end up with this 1 over what I want is equal to a number, and my experience has been that messes up a lot of students. So let's try doing this one on the calculator as well. I'm going to say, well, 1 over x is equal to 0.255 times 2,000 plus 100. We'll do the num solve. I'm going to clear this out. Oh, missed the button. There we go. So on the left, I have a fraction, 1 over x. I would encourage you to use this fraction button. Makes it look like a fraction, less confusing. So 1 in the numerator, and I want my x in the denominator. Then I'm going to move over to the other side of the equal sign, 0.255 times 2,000 plus 100.
That's what Max did.
Yeah, it's choking.
Yeah.
Max iterations error. So there's 2 things that your calculator will sometimes say. Max iterations error or no sign change error. And what this means is that it can't do it starting at x equals 0. Because we've got 1 over x, right? And if x is 0, that's undefined. That's not a great place to start. So what we're going to do is we're going to press clear, and our equation's fine, but let's start with something else. Let's start with 1, maybe, right? You can do it. I believe in you. Come on. You can do it.
It's still choking.
Yeah, mine's choked
You're
up.
still choking? Okay, so now I got no sign change error. So now what do we do? Well, let's think about this. What was the initial concentration? On the y-axis, it shows us the intercept is 100. That's 1 over the initial concentration. The initial concentration was 0.1. So let's try that. There we go. 0.001639344. Okay? So that does illustrate both of the issues that you might come up with using the number solver correctly. You got the equation typed in. If you make a mistake in the equation, then you've got other problems, right? The equation was correct, but it was choking on us because we weren't giving it a good starting point. Okay? So if one doesn't work, try a positive number. If that doesn't work, some things might have a negative number. But a good guess is think about, well, what reasonably might the answer be? Well, it's going to be less than 0.1, right? So we know that 0.1 is in that ballpark of where the answer is, so we'll feed it that and let it get started. So whether you use this or not is really a very personal choice. And some people may want to use the number solver in some situations and not in other situations, just depending on how confident you feel about doing the algebra for the particular equation. Any questions about that? So I would want to report this answer with 3 sig figs. So I'd round the 3 up to a 4, and then the units on a concentration are always going to be molarity. Is that what the book says? Yes. Oops. Questions? Yeah. Can you leave it as a fraction? No, you can't. Because if you try to enter 1 over 610 as the answer in Mastering Chemistry, it's going to say that's wrong. Does that make sense? Well, that's not a proper answer, right? If I, let's see, how old are you? Well, I'm 30 times 2. That's not how people answer, right? You need to do the math and give a single number as your answer. Okay. Any other questions? What am I doing here? Okay, so we did first and second, and now we're going back to 0, following this same pattern. And by the way, I'm showing you how these things are derived. I'm not going to test you on that, okay? But the rate is equal to the rate constant times the concentration of A to 0 power, which means that the rate is equal to the rate constant. We can also define the rate in terms of the change in concentration. So we get this guy, and we integrate that, the magic of calculus, and we get this. Again, written in the form of a linear equation. So this tells us that Y is our concentration and X is our time. And the slope will be equal to negative K. So again, if we want to know what K is equal to -1 times the slope. Okay? And we're not going to do an example of that one. We're going to talk about the half-life of a reaction. So half-life means the time needed for half of the reactant to react, for the concentration to fall to 1/2. So if the initial concentration is 0.5 molar and T1/2 is 50 seconds, what will the concentration be after 50 seconds? 50 seconds is the half-life. So the concentration is, 0.12 or 0.25, right, is half. 1/2 times 0.5, 0.25 molar. And then after 100 seconds, it's going to get cut in half again, right? So we multiply by 1/2 again, we cut it in half again, and this is where we get the 0.125. Does that make sense? So you did learn about half-life in Chem 3A. You may or may not remember that. We don't get all of the reacting in 2 half-lives. You say, well, the first one, it cut in half. The second one, that would be the rest of it. No, it doesn't work that way because the rate changes with the concentration, right? So we can write an expression for the half-life, and it's going to be different for the different reaction orders. So here's the integrated rate law for first order reaction, and this is the same as the one we were looking at. It's just been rearranged to make it a little easier, but it is the same thing. So they took this guy and rearranged it. So we're trying to find an equation that gives us T, the T1/2. So when T is equal to T1/2, we know that the concentration at that time is 1/2 of the original concentration. Do we know what the original concentration is? No, we don't, but we know that it's now half of that. So we can plug that in. Instead of writing A sub T, we're going to write 1/2 A sub 0 divided by A sub 0 is equal to negative KT. And this would be all in parentheses. So this fraction can be simplified, right? We've got this unknown variable on the top and the bottom, so we can cancel those out and say, well, the natural log of 1/2 is equal to negative K, and this would be T1/2 now. Well, what's the natural log of 1/2? That's what we've got calculators for. Negative 0.693. There's a bunch of other digits. They traditionally just use the 3 sig figs. So negative 0.693 is equal to negative K times T1/2. T1/2 then is equal to negative 0.693 divided by negative K. T1/2 equals 0.693 over K. The half-life of a first-order reaction does not depend on the initial concentration. I'm not going to make you derive that on a test or anything. But that's where that equation comes from. So here we're looking at concentration versus time for a first order reaction. We see that the concentration goes down. If it starts at 1 molar, it'll be cut in half after 1 half-life. Here the half-life is 100 seconds. And so when you go another half-life, it gets cut in half again from 0.5 to 0.25. When you go another 100 seconds, it gets cut into half again, 0.125. So every 100 seconds, the concentration is cut in half. How long does it take until it's gone? Well, if you're going to count gone as 0 molecules, it might be a pretty long time. If it's gone as in there's too few to detect that they're there, then it's not going to be as long. But it's just going to get cut in half. So the half-life here is independent of the initial concentration. A0 doesn't show up in here at all. So this half-life is constant, and that's unique to first-order reactions. In Chem 3A, you learned about radioactivity and how radioactive isotopes decay, and they do that according to a first-order reaction. Okay? So this describes what happens in radioactive decay. Okay, the images here are showing a first-order reaction, A to B at various times. Now, this is where, on the slides, it uses color, which doesn't work so great on the printed page, right? So what you might want to do is like draw a circle around the red ones on your paper so that you can see what's going on. Note to self, I need to change this slide. So the black circles represent the reactant, the circled circles represent the product. What's the half-life? So initially we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of the reactant molecules. How many will we have after one half-life? 5. So we want to find the one that's got 5. Well, that looks like more than 5. That's more than 5. 1, 2, 3, 4, 5. Here we've got 5. So the original number got cut in half, so this is the half-life. Any questions? Yeah.
Can you explain that again?
Yes.
So how you got the, is it, what are you looking into get?
So what I'm looking at, I'm thinking about the definition of half-life. Half-life is the time for the concentration to be cut in half. So here's my original concentration represented by 10 circles.
Okay.
Yeah. So I'm looking for 5 circles left. Thank you for asking. Anybody else? Questions? A first-order reaction has a half-life of 25 minutes. If the concentration of A is 0.3 molar, what's the concentration of B after 50 minutes? Do not use a calculator to solve this problem. We don't need a calculator because the numbers are nice here, right? So what's our half-life? It's 25 minutes. Well, how much time are we talking about? How many half-lives is that? 2 half-lives. In the first half-life, it gets cut in half. The second half-life, it gets cut in half, right? Oops. Didn't mean to do that. So we start with 0.3, and after 25 minutes, it gets cut in half to 0.150. And then if we go another 25 minutes, it's going to be 0.075. Did I do that right? Yeah. I know. So it's like I'm doing that, and I'm like, wait a minute, that's not one of the choices. So then we need to think a little bit here. This is the concentration of A at 50 minutes. What is the question asking us? What's the concentration of B? So I started with 0.3 molar A, and now I've got this much left. What happened to the stuff that disappeared? It turned into B. And this was a 1-to-1 stoichiometry. So what we're looking for is 0.3 minus 0.075. 0.225. And that's the concentration of B. So that is a question with a trick in it, right? There will be some questions like that. And so this is one where you can't really just like plug it into the calculator and have an answer, right? Because there's not really an equation for this. We need to be able to think about what's happening. We need to understand stoichiometry, right? That 1 mole of A makes 1 mole of B. So here, when I lose 0.15 moles of A, I'm going to gain 0.15 moles of B. And here, I'm losing 0.075. I'm going to gain 0.075. I think the best way to answer it, though, is to find the concentration of A at the end and then convert that into B. Any questions? First order reaction is a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? There's 2 ways you could solve this one. Because they're talking about 1/8, the numbers are nice. So we start with 1, and then we go to 1/2, and then we go to 1/4, and we go to 1/8. 1, 2, 3. That's 3 half-lives. So 3 times the half-life of 26.4 seconds. .2 seconds. You can use the equation to do this as well. The natural log of AT over A0 is equal to negative KT, 1/2. The problem with going this direction is they're not telling us what the reaction, the rate constant is. Could we figure it out? We could, but it's going to take longer. It's going to be kind of circular. So this is the best approach for that problem. Any questions? To figure out what the rate constant would be, we would use T1/2 is equal to 0.693 over K. We know what the half-life is, so we can calculate K. And then we could go up here and we could plug K in. Wait a minute. This should not have half in it. Sorry about that. And we want 1/8 of the initial value. So that's saying that AT is equal to 1/8 of A0. So conceptually, that's more difficult. Any questions? Second order rate law. Here's our integrated rate law. Again, we can find the equation for the half-life by recognizing that AT is equal to 1/2 of A0. So this is 1 over 1/2 of A0 is equal to K T1/2 plus 1 over A0. So I'm going to subtract 1 over A0 from both sides. And 1 over 1/2 is the same as 2, right? So we could write this as 2 over A0. So that gives me 1 over A0 is equal to K T 1/2. So the half-life is equal to 1 over the rate constant times A0. Again, I don't expect you to remember how to derive that. Any questions? So here the half-life is going to depend on the initial concentration. If we start with a lower initial concentration, we're going to have a longer half-life. And as the reaction proceeds, the half-life gets longer and longer and longer. There's the zero integrated rate law to find the half-reaction equation, the half-life equation. We're going to put this in there. So 1/2 of A0 is equal to negative KT plus A0. Most people are going to think about subtracting A from both sides. So that gives me negative 1/2 A0 is equal to negative KT 1/2. And I'm going to divide both sides by negative K. So T 1/2 equals the concentration of A0 divided by 2 times K. Did I do that right? Yes. Doubted myself there for a minute. So with a zero order reaction, the half-life also depends on the initial concentration, but the half-life is shorter at smaller concentrations. And the half-life gets shorter as the reaction proceeds, unlike a second order where the half-life gets longer and longer. So this is a summary of what we've talked about. If you look at the useful information for Chem 1B exams that is found at the last page of your lab manual, you'll see that a lot of these things, a lot of these equations are in there. They're just not labeled, but they're kind of in the same arrangement. So you'll see that they're on top of each other, and next to, they're in this same arrangement on there, just not labeled. Okay. Decomposition reaction with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration. Which statement is most likely true for this reaction? So it's talking about a graph, how the half-life changes, or how the rate changes. So those choices are hard to compare. So for a question like this, I think it's best to answer the underlying question first. What's the order of this reaction? Is it first order? No, because the rate slows down, it changes. And the half-life depends on the initial concentration. It's not first order. Is it 0 or second? Second order. The half-life gets longer, right? The rate slows as the reaction proceeds. So from the word description, we can tell that this is a second order reaction. Now we can better look at the choices. Natural log of concentration versus time is linear. Is that true for second order? No. What's that one true for? First order. The half-life increases as the initial concentration increases. My brain says, I don't want to think about that one. A doubling of the initial concentration reacts in a quadrupling of the rate. Is that second order? That's second order. So then, kind of knowing that this is wrong, we could go back and think about that a little bit and say, no, that's not how it works. So you could see a question like this on an exam. This requires you to understand some things, right?